Hi, everybody. How is everyone doing this weekend? Hope you're all staying safe and healthy. So today I would like to talk about the one sample t-test, and it sort of is a precursor to the PowerPoint on the two sample t-test, or the independent sample t-test that is posted. So I want to talk about this. We're going to go through the kind of the nuts and bolts of performing a one sample t-test, the difference between a t-test and a z-test, and also a few housekeeping things to start off with. So as the slide says, you're going to need, for this lecture, you're going to need a printout of the slides and or a sheet of paper or notebook to take notes. So be really beneficial for you to do this and to take notes and then ask questions when we get together on Tuesday. You'll need the t-distribution table, and this was also attached to the announcement. The announcement for all of these items was entitled One Sample T-Test and Stuff, I believe. So everything should be attached there, including the link to this lecture. You'll need both of the worksheets. The worksheets say example 1 and example 2. Okay, so a little bit of info about Project 2. Project 2 will now be due Friday, April 3rd at 11:59 p.m. You are welcome to turn it in anytime you'd like. You will be assigned groups. In fact, I sent out a table, a recent announcement regarding the project. I sent out a table as an attachment that shows your group assignments. Please take note that if you choose to work on your own, please let your group members know, okay? So they're not waiting on you or thinking that you're not, contributing. That can be frustrating. So just communicate with your assigned group, please, if that's the case. I provide more details in that announcement and all the attachments that are needed. So, take a look at those and look at the example article that I posted. And then the first part of Tuesday, we will, I can answer questions about that. And then I'll have you get to your groups or yourself and work on the project. And then, of course, I'll be here to facilitate and answer questions if needed. Okay, so that is the long and short of it. And so let's jump into one sample t-tests. First of all, we need to talk about the differences and the similarities between the z-test and the t-test. Now, one of the questions that you're going to need to address is, when given scenarios of research studies, when should you use a t-test instead of a z-test? So what are those characteristics to look for? Well, the one sample t-test is used to test hypotheses concerning a single group mean selected from a population with unknown variance. So let me just emphasize an unknown variance. What does that look like? It means that there is no standard deviation for the population. Okay, so if that is missing, then that should tip you off that you need to run a one sample or single sample t-test. So in other words, when we don't know the population standard deviation, what we're going to do is estimate that standard deviation, or estimate the variance for that. And we're going to use a sample standard deviation, right? So we're going to run through the calculations for a sample standard deviation. We did that a long time ago, but we'll refresh it again today. So the t-test versus the z is appropriate because behavioral researchers rarely know the value of the population variance. Okay, so rarely do we know much, if anything, about the population mean, and especially in this case, the variance. So here's a chart that I believe is helpful, just talks about or just illustrates the differences. Once again, only breaks it down into the fundamental pieces of the t-test and the z-test hypothesis test. So one characteristic is the obtained value. So at the end, when we're calculating our mean, what is the value that we obtain? Well, we obtain a z-statistic and a p-value, okay? For a t-test, we obtained a t-statistic and the same thing, a p-value. What distribution is used to locate the probability of obtaining a sample mean? Well, for a z-score, z-statistic, we will use a normal distribution, right? Because when we transform our raw scores into z-scores, automatically we'll form a normal distribution with a mean of 0 and a standard deviation of 1. However, because we're taking a sample, okay, a group of scores from that distribution, then that creating another distribution with that sample, it becomes a t-distribution. What is the denominator of the test statistic? The denominator is standard error for z and estimated standard error for a t-test. Do we know the population variance? For a z, we do, and for a t-test, we do not. The sample variance is used to estimate the population variance. Are degrees of freedom required for this test? No, for a z-test. And yes, the degrees of freedom are n-1. Anytime we're using a sample to calculate variance, we must use the degrees of freedom, n-1. What does the test measure? The test measures the probability of obtaining sample outcome, excuse me, for both a z-test and a t-test. And what can be inferred from the test? Well, whether the null hypothesis should be retained or rejected. And the same thing goes for a t-test. So we're essentially trying to find the same thing. We just have a little bump in the road, which is that we do not have the sample, we don't have the population standard deviation. And one little note here. So when we talked about originally talked about hypothesis tests, we talked about using, fail to reject the null hypothesis. And that is actually, I like that way of talking about it. It's a little more consistent with the statistical, the probabilities, and putting those into a concise wording. That said, your textbook likes to use the word retain. So fail to reject the null hypothesis is the same thing as retain. So we'll stay consistent to the textbook and use retain instead of fail to reject the null hypothesis. Okay, so I think this chart will be helpful for you down the line. You can use it when you're studying or when you're actually taking your test. It just gives you some basic answers and comparisons between the two tests. So we have that understanding before we start calculating everything. Why is a t-distribution associated with degrees of freedom? All right. So if you remember that the degrees of freedom are the scores that are free to vary, okay? And so when we have scores that are free to vary, there's always going to be one score that is not, because there's a fixed sum, okay, of scores. So in other words, when we have a sample and there's only an n of 5 or an n of 10 or n of 100, that's fixed, right? That's not something that continues into infinity like the population. The sample is is not infinite. So let's look at this. So degrees of freedom. So the larger the number of degrees of freedom, the more likely our sample distribution is going to resemble the original Z distribution, which was the standard normal distribution. This is kind of like the standard. This is kind of like what we aspire to get to, right? But when we take a sample, we don't really know where the sample came from. And so, so it's going to have less variability, okay? Because if you take a sample of 5, okay, you have very limited number of scores, okay? And when you have a limited number of scores, it's less likely that those scores or the mean of those scores is going to be generalizable to the mean of the whole population versus if you have 100 scores. So for example, since the t-distribution is based on sample size, we have to take n-1 in order to correct for that overestimation. So the green here is a t-distribution that's smaller than 30, okay, an n of 30. The red is a t-distribution that's close to 30. And then you can see how all of those start approximating the actual shape and variability of the Z distribution, which is what we aim for, because then we can say that our sample closely resembles our population. Okay, so the pattern is that the larger the sample size, the more likely our sample is going to resemble the normal distribution, the Z distribution. Okay, so these t-distributions is a normal-like distribution with greater variability in the tails than a normal Z. And you guys can see that here from this illustration, there's greater variability. The sample variance is substituted for the population variance to estimate the standard error. So we're going to have an estimated standard error because we're going to use the values from the variance from the sample and then estimate those to the population. So once again, we hope that those the variance from the sample is close, similar to the variance from the population. And one of the ways we do that is to increase Rn. So as sample size increases, the degrees of freedom increases, and the sample variance more closely estimates the population variance. So here are the steps for the one sample T hypothesis test. We state our hypotheses, we have the null and the alternative hypotheses. We're going to set the critical region. So we're going to use that T table that I attached to this announcement. The T table is part of a packet of tables. I know that I've provided this for you earlier on in the semester, but you can use whichever one. There's also one in the back of the book, which is in the appendix in the back of the book. It is one page, so it's easy to use. It's pretty user-friendly compared to the unit normal table. I believe it's, is it 2B, or it's the unit normal table is the first in the packet. I think it's 4 pages. And so page 5 and the next page is the t-distribution table. So you want to get that out right now. You can pause this and make sure you have that out or pulled up on your computer. So we're going to need to use the t-table to set the critical region. Our calculations, we have a few. We will calculate the estimated standard error first, then we'll calculate the actual t-statistic, we'll calculate the effect sizes, which there are 2, and then we're going to make the decision about the null hypothesis. So in other words, we're going to reject or retain the null hypothesis. So about the effect sizes. So we did talk about the Cohen's d for the chapter before this. So the Z-score or Z-statistic test. So the estimated Cohen's d okay, is a measure of effect size in terms of the number of standard deviations that mean scores shift above or below the population mean. So the larger the D value, the larger the effect in the population. So the Cohen's D, or for the t-test, the estimated Cohen's D is going to measure the size of the effect. Okay. And we're going to standardize that size of the effect, which is the mean difference, the absolute mean difference, okay, so that we can say that this effect, okay, in this mean actually fell, 0.92 or 0.553 standard deviations away from the mean or above or below the mean. So it's just measuring the effect in terms of standard deviations. So for example, we can say that we obtained an estimated Cohen's D of 0.85. What this means is that the mean score shifted 0.85 standard deviations from the population mean. If the Cohen's D was 0.25, the mean scores only shifted a quarter of a standard deviation away from the population mean. Okay, so we Cohen's D, we want Cohen's D to be big, a big effect size, because the farther away that our mean falls from the population mean, the more likely we are to reject the null hypothesis. And just a note, we did use Cohen's D for the z-test, and we'll also be using it for the t-test, for both t-tests, the one that we'll talk about today, and then the independent sample t-test on the other lecture. So here's a new a new effect size, right? So it's called R squared, the proportion of variance. In your textbook, I noticed that they explained that the proportion of variance is measured in a t-test by eta squared. Okay, so if you've read the textbook or peruse the textbook, you'll see in chapter 9, when they're talking about proportion of variance, they actually use eta, okay, which is a different Greek letter, right? But in other cases, you'll see R squared is used, and either is fine. So we're just going to use R squared. So here's the effect size formula. Now, what is the proportion of variance? It is a measure of effect size in terms of the proportion or percentage of variability in a dependent variable that can be explained or accounted for by the treatment. So is there a better way of talking about that or of stating that? Sure. So we could say that our treatment accounted for whatever percentage, so let's say 40.48 or 48% of the overall effect. Okay, so let's take a look at this. If we obtain an R squared of 0.48, we can say that our treatment accounted for 48% of the effect. Okay, and that also means that something else like error or confounding variables may have influenced the other 52% of the effect. So once we make a decision about our null hypothesis, there's always the Cohen's D and there's always the R squared that will give us a more deeper understanding of that effect, whether how big or small, or whether how much of our treatment actually caused, okay, or influenced the effect of the dependent variable that we're trying to measure. So let's try the example from worksheet 1. So if you can find worksheet 1, there should be 2. Worksheet 1, there's a number 1 at the top, and it's about the effect of a new reading program for second grade students. So go ahead and pull that up right now, and I'm going to do the same thing. Okay, so so let's read this. All right, so a researcher would like to evaluate the effect of a new reading program for second grade students. Over the past 5 years, a standardized test given at the end of the second grade has produced a mean score of 45. A sample of 25 students is placed in the new program, and at the end of the school year, they obtain a mean test score of 51 with sum of squares of 9,600. And by the way, sum of squares is needed to calculate any sample variance. We did that back before the first test. I don't know if you remember, but just to reiterate what that is for, the sum of squares is necessary in order to calculate the variance of a sample. Okay. Okay, so based on these data, can the researcher conclude that the new program has a significant effect on reading scores? Okay, that is the question that we need to focus on, okay? This gives us the answer to some other questions before we start our test. This is a two-tailed test because the term effect is non-directional, okay? Effect is non-directional. Other non-directional items would include change or different than. So what that means is we don't care if the effect of the program is better or worse, has increased reading scores or decreased reading scores, as long as it has shifted far away from the population mean in either direction. So we'll state the hypotheses first. Our null hypothesis is that the population mean is equal to 45, and our alternative hypothesis is that our population mean is not equal to 45. All right, we use the equal sign because we are doing a two-tailed test. Okay, the second step is to set the critical region. So first of all, we need to find the degrees of freedom. And in this case, we look at n minus 1, n is 25. So our degrees of freedom is 24. Okay, then we use the t-table. So if you want to get out your t-table, and I'm going to pull up a screenshot of that as well. So get out your t-table. I'll show you what it looks like in case you haven't looked at it yet. Okay, so first of all, let's take a look at this. So we use the t-table to locate the degrees of freedom, so we know those are 24, and then we find the appropriate column, and from there we can find the critical value, okay? So what exactly does that look like? Let's take a gander here. Okay, so this is the part of the t-table, I'd say most of the t-table, and everything that you would need. So please make sure that you have this so you know how to use it. On Tuesday, we had several questions about this just for clarification. So if you have questions about how to use this, please jot them down and ask them on Tuesday when we meet. Okay, so we have degrees of freedom of 24, right? So degrees of freedom of 24. Now, sorry about that. We are also looking at a proportion in two tails combined in this row at the top, and our alpha is always going to be set at 0.05. So we're going to take our degrees of freedom And we're going to kind of just go across and go down. And we're going to end up with, sorry, just messed something up. So we're going to go across for 24, and we're going to go down from proportion in two tails, okay, 0.05, and we're going to get a 2.064. That is our t-test, which will indicate our critical value, which of course is the boundary between the critical region and the rest of the distribution. Okay. Now, had we had the same values in the same scenario, but it was a one-tailed test, so we would still go to degrees of freedom of 24 if we're using the same values, but we would use this top row because it says proportion in one tail. So we take our alpha, which is 0.05, and we'd move down to 24, and it looks like 24 proportion of one tail would be 1.711. But today it's 2.064. One other word about this is that 2.064 is going to be on both tails. So we don't have to divide it by 2. This table already does it for us by saying proportion in two tails combined. So it's already done the work, okay? So you have 2.064 on one end and 2.064 on the other end. Okay, so back to here. So we have two positive or negative 2.063, and we're going to place them in the tails of the distribution. Okay. And note, as always, our alpha level will be set at 0.05. Okay, so we have our critical region. So the next step are the calculations. So the first thing we do is the sample variance, and this is where we use our sum of squares and our degrees of freedom. So I've given you the sum of squares. If you go up to the very top, you'll see that the sum of squares is 9,600. And so we'll scroll back down. 9,600 divided by 24 degrees of freedom equals 400. That's the sample variance. In order to get the standard deviation or the sample standard deviation, we take the square root of 400 and we get 20. So 20 is our standard deviation, and that's going to come in handy in a couple of the subsequent formulas. So then the second step for calculation is to calculate the estimated standard error. And again, we use the word estimated because we don't have the population standard deviation. And so we're estimating that by using the sample variance and the sample standard deviation. So here is the formula. So lowercase s, standard deviation for the sample divided by the square root of n. We know that our standard deviation is 20 divided by square root of 25, which was our n, and that gives us 5. And so our estimated standard error is 4. Okay. And then we have our one sample t formula. So it looks like this. M minus mu over the estimated standard error. Okay, very similar to our z-score or z-statistic, except that, of course, we have our estimated standard error here. So if we just plug in our numbers, 51 minus 45, which going up here, see 51, okay, and then 45 is the population mean. So we have that information. We plug it into here, we divide it by 4, and we're going to get a positive 1.500. And just quickly moving up to here, does positive 1.500 fall into our critical regions? And the answer is no, so we know already that we're going to retain the null hypothesis. In other words, the null hypothesis is true. So we have two more calculations, the effect sizes. So we have an effect or we don't have an effect, but either way, we still want to calculate these two values. So Cohen's d, once again, is going to tell us how big or small our effect is. And so here's the formula. The mean differences divided by the standard deviation for the sample. Now, the mean differences, I've mentioned this before, it's best, well, I prefer to use the absolute mean difference. And that's just because I'm not going to have you interpret it, okay? And you're going to get a positive number. If you're moving on to, if we had if we end up with a negative mean difference, then of course we'd have a negative Cohen's d, and then your interpretation would be more specific. You would say, this is if the Cohen's d is 0.30, you would say that your sample mean was, fell at 0.30 standard deviations below the population mean. Okay, but we're not going to be interpreting that. So in this case, let's keep just the absolute mean difference, and we get 0.30 for Cohen's d, which is pretty low. Then our proportion of variance, which is r squared. We have our t squared divided by our t squared plus the degrees of freedom. I didn't show all of the formula, all of the calculation, because I presume that you'd be able to plug in the correct numbers from up here and calculate the proportion of variance, okay? So we make a decision. So the fourth step is to retain the null hypothesis. The new reading program did not have a significant effect on reading scores. Our t-statistic, and don't forget in parentheses, we have to put our degrees of freedom. So whenever we're using a t-statistic, the degrees of freedom are essential to calculating our t-statistic. So not only does this give us an idea or tell us what the degrees of freedom are, but it also tells us what the overall n is. So the t is positive 1.500. P-value is greater than 0.05. The Cohen's d is 0.30, and r squared equals 0.09. Okay, so we're just plugging in those numbers. So here's a note. The p-value greater than 0.05. There's a reason why it's greater than. The p-value is greater than 0.05 because we retained the null hypothesis, which means that there was more than a 5% chance of committing a type 1 error in this test. In other words, there was a greater than 5% chance of of getting a false positive, or saying that we would reject the null hypothesis when the null hypothesis was true. In other words, we would say our treatment had an effect when in fact it didn't. So it was more likely that we were going to do that in this case, okay? And so there was more error actually built in than just the set 0.05 that we set ahead of time, okay? So all of these steps, these are all the steps for the hypothesis test. You'll be expected to know these. I'll be giving you some other examples down the line, but this is really important. These should be downloaded or printed out, okay? And I am going to give you one more that we'll walk through just so we know, kind of feel okay with everything else, okay? Oh, why is this paused? Sorry, let me go back to this. I am not sure why this paused. I'm not sure how long it paused, but I know we were talking about critical region. okay? And our degrees of freedom, we already set our alpha level. So then our calculations are as stated here. If you have your sheet, which you should have in front of you, worksheet, I'm sure you're able to follow along. But anyway, I'm sorry, I think my screen share was off at that point. So here is what you would have been seeing, and it was just the calculations. So we're gonna do another example, and we'll run through the calculations in real time so that you'll be able to make notes and be able to follow along in real time while seeing the actual screen on Zoom. Okay, so let's go to our second worksheet. Okay. The second worksheet is also an independent t-test. I'm sorry, a one sample t-test, and it's about memory rehearsal. So I'm gonna jump back down here, and I'll give you a minute to pull up all of your stuff. Okay. Okay, so this is what your scenario is. So when adults are given a set of items to hold in memory, they automatically rehearse the items to prevent forgetting. Young children, however, do not spontaneously use rehearsal. As a result, when given a small set of items to remember, 2-year-old children on average can recall only 2 items. A sample of 16 children is obtained, and the children are trained to use rehearsal during a memory task. After training, the children in the sample show an average recall of 4.3 items with sum of squares of 60. So based on these data, does rehearsal significantly improve memory in 2-year-old children? This is a one-tailed test because a directional term, improve, is used. So words such as improve, increase, decrease, faster, slower, all of those would warrant a one-tailed test. You're going one way or another. So your first step is to state the hypotheses. Okay, so let's look at this in a little closer here. So our null hypothesis is the population mean is less than or greater than 2. Our alternative hypothesis is the mean is greater than 2. Now this is another concept where I had lots of questions on Tuesday. So how do you know when, why, and how to use the directional symbols here instead of just equal or not equal to? Well, if you have a one-tailed test, if you're using a directional term, okay, like this one, improve, then you are going to use the directional symbols. What I like to do is take the the alternative hypothesis first, because the alternative hypothesis is what I want to find. It's in my research question. So I want to know if rehearsal improves memory. All right. So then I'm going to put a greater than sign because I want my sample mean to be greater than 2. Then I know the rehearsal helped. Then all I need to do for the null hypothesis is use the opposite directional symbol and remember to use the equal to sign as well. So null hypothesis is less than or equal to 2. What that means is that after the treatment, my sample mean actually comes out as less Pin 2, well, meaning it's going the opposite way, that rehearsal decreases memory, or there's no difference, that rehearsal does nothing. Okay, so this is what I want right here. Okay, yes. So here we go, setting the critical region. First, like before, we're going to find the degrees of freedom. Okay, n-1. If we go up to here, we see that our n is 16, so we just plug that in. 16 minus 1 is 15. We're going to go over to our table, and we're going to locate the degrees of freedom of 15, and then look in the appropriate column, again, where alpha is 0.05. Okay, so if we look in that column again, we're going to find that the critical value is 1.753. And let me just pull that up quickly so that we can see and make sure that we're all feeling okay about it. Okay, so let's do this. Okay, so degrees of freedom of 15 right here. All right, and so I just cover that up. And then we're looking in a proportion in one tail. So one tail, and at an alpha of 0.05. So that means we're going to go down here to 16, okay, and sorry, to 15, excuse me, and we're going to find that our critical value is 1.753. So then we'll go back to our example, and we're going to write positive 1.753. It's all in one tail, and so that's where our critical region is. Okay. All right. Once again, just keep in mind the alpha level will always be set at 0.05, just in case you forget or you accidentally use the wrong column. Make sure you always know that the alpha will be 0.05. Okay, so here are the calculations. We have our sample variance. Our sample variance is sum of squares divided by degrees of freedom. If we move back up here, we see that the sum of squares is 60, right? And that our degrees of freedom we know is 15. So 16 divided by 15 is 4, and then the square root of 4 is 2. So we have our standard deviation. That's going to come in handy in a couple more calculations like this one. So our estimated standard error is standard deviation for the sample divided by the square root of n. Our standard deviation for the sample is 2, and the square root of 16. Okay, so remember our n was 16, which is up here. So our n was 16, and square root of 16 is 4. So our estimated standard or denominator is 0.50. So that's going to go in the denominator. Here's the one sample t formula. We take our mean difference divided by our estimated standard error. Sample mean was 4.3 minus the population mean, which was 2. Divide that by 0.5, and we have positive 4.600. 4.6, does that fall into the critical region? Yeah, it falls way into the critical region, right? So that means we can reject the null hypothesis. So we have our decision, okay? We're not quite done yet, right? So we have our effect sizes. So we have our mean difference, and for the sake of us, in our class, we're gonna just take the absolute difference, which is 4.3 minus 2, okay, and that's divided by 2, and that's going to give us 1.15. Okay, so I didn't do all of the calculations here in between. I know that you can do it in your head. If you need your calculator, that's fine. But 4.3 minus 2 is 2.3. 2.3 divided by 0.5. Oops, where was that at? Sorry, here we have 2.3 divided by 0.5 is 4.600. Okay. So then we go down here, our Cohen's d is 4.3 minus 2. All right, so again, it's going to be the same mean difference is 2.3 divided by 2, 1.15. All right, this is a pretty big Cohen's d, which makes sense because we rejected the null hypothesis. Then our proportion of variance accounted for. Again, I skipped over some of that easier math. You can plug in, right? You can plug in those numbers yourself, but if you're going to get 21.16 divided by 36.16. And so our proportion of variance, or our R squared, is 0.59. Okay, so step 4, we make our decision. We reject the null hypothesis. We say that rehearsal significantly improves memory in 2-year-olds. We have our t-statistic with our degrees of freedom in parentheses. Our t-statistic is positive 4.600. Our p-value is less than 0.05. Our Cohen's d is 1.15, and our R squared is 0.59. So here's another note. The p-value is less than 0.05, right? Less than, because we rejected the null hypothesis. There was less, what it's saying to us is that there was less than 5% chance of committing a type 1 error. In other words, there was less than 5% chance of saying that the null hypothesis was, rejecting the null hypothesis, or saying there was a treatment effect when in fact there really wasn't. Okay, so that's good news that we actually, that the test was set up well enough that even when we were setting our alpha level at 0.05, the test was able to detect a big effect, meaning that actually 0.05 was too large. We could have gone down to 0.04 or even 0.03 and had just that little bit of unlikelihood for scores to fall in there. And still, it's likely our scores were to fall into or beneath a 0.05. Okay, so that is really good, because that means it'd be farther out from the population mean. And post-treatment, that's what we want. That is our ultimate goal. And in statistics, is that after our treatment, we want our test statistic to fall as far away into the tails as possible. So if you have questions, I urge you to jot them down. We will start class on Tuesday answering those questions, and then we'll get on with our project. And as another reminder, the project was originally due Wednesday night on the 1st, but I changed that to Friday night. And only the main reason is because you'll be working with groups, or most of you will be working with groups. And I know that it can be difficult to work with groups outside of class and to track them down, group members outside of class tracking them down, or making sure you'll contribute, et cetera, et cetera. So that will give you an extra few days to get a hold of your group members and work together. Okay. Okay, so that about does it for the single sample or one sample t-test. And if you haven't watched it already, the other lecture is the independent sample t-test, or independent measures t-test. And that one actually has 2 samples instead of 1. Okay, so enjoy the rest of your weekend. Stay inside as much as you can. and I look forward to seeing you on Tuesday. Okay, bye-bye.